This is the intro video for Calculus AB, and we'll be looking at estimating and finding the area between a curve and the x-axis. So the goal of this video is to help you understand what a left, right, midpoint, and trapezoid sum are, and then we want to also get some good thoughts on the accuracy of left sums and right sums. So there's four of them here, and so we're going to run through the four of these. And when you get to class, we'll try to use these ideas to help us not only estimate areas, but also to consider the accuracy of those estimations. The first one is a left sum. A left sum uses rectangles whose height is determined by the left side of each interval. So essentially what we're going to be looking at is how you could estimate the area between the x-axis and a curve like this using rectangles. So a left sum is going to use the left side of the interval to determine the height. So maybe we would take this region from 0 over here to 8, and we could split it up into a certain number of sub-intervals. Maybe we'd split it up into just 4. So maybe this would represent one sub-interval, there's our second, there's our third, and then our fourth is off to the side there. So we could write our rectangles, we could draw them in a number of ways. A left sum is going to use the left side of the interval to draw the height in. So for the first interval over here from 0 to 2, my height is going to be determined by the left side of the interval. So my first left sum rectangle would look like this. Well, the next one, from 2 to 4, we would use the height based on the left side of the interval. So that would be this height. And then from 4 to 6, the left side height would be determined by the height at 4. So that would be up here. So that left sum rectangle would look about like that. And then from 6 to 8, we'd be looking at the height there at 6. And so please notice that all of these rectangles have a height based on the height of the curve on the left side of the interval. That's why they're called left sums, or left sum rectangles. So if we were going to try to estimate the area under the curve here, we would just find the areas of those rectangles, add them up, and that would be our estimation. So thoughts on accuracy. So maybe you noticed that on this first stretch from 0, x equals 0 to x equals 4, maybe you noticed that the graph here is increasing. And if the graph is increasing, maybe you can see that those left sum rectangles fall below the actual curve. So I would say if the graph is increasing, a left sum will be an underestimate. In other words, the areas of these two rectangles right here certainly would be an estimate for that area from 0 to 4, but they would be too low, right? They would be an underestimate. And then if you were to look at the interval from 4 to 8, so this purple interval here, you can see that the graph is decreasing. And you can probably also see that those left sum rectangles are above the curve, or at least partly above the curve. We're talking about these little parts up here. These little segments of the rectangles are too much, right? So we would say if the graph is decreasing, a left sum will be an overestimate. Okay, so that's a left sum, and we're going to now look at a right sum. So right sums use rectangles whose height is determined by the right side. Hopefully that's not a surprise. Okay, so again, same kind of thing. We're going to estimate the area from 0 to 8, and just to make it easier on ourselves, I'll split this up into those 4 subintervals again. So from 0 to 2, and from 2 to 4, and from 4 to 6, and then from 6 to 8. So if we're going to use the right side of the interval, then my first rectangle's height would be determined by the height at 2. So I could build this triangle and draw it in like so. So that'd be my first right sum rectangle. My next one would be based on the height at 4. You can see that that right edge of the interval is telling the rectangle how high or how tall it needs to be. And then the height of the curve at 6 would tell this rectangle how tall to be. And then the height of the curve at 8 would tell that rectangle how tall, there we go, it needs to be. So that last one would look about like that. Okay, so again, if we found the area of all these rectangles, added them up, that would be our approximate area under the curve. We can clearly see it's not going to be perfect, but it would be an approximation. So thoughts on accuracy. Same kind of thinking here. Perhaps you can see that on this green interval, our graph is decreasing. And you can probably also see that those 2 rectangles approximating that part of the graph are well under, right? They're an underestimate of that area. So we would say if the graph is decreasing, a right sum is an underestimate. And likewise, on this blue interval, you can see that the graph is increasing, and we have kind of the reverse situation happening, where those rectangles are too high. You can see that overestimate part right there. So we could say, in general, if the graph is increasing, a right sum is an overestimate. Okay, so we did a left sum, we just did a right sum. Now we're going to move on to the next two, the last two. The next one here is a midpoint sum. So midpoint sum use rectangles whose height is determined by the midpoint of each interval. So this is not a situation where we're using the left edge, like a left sum, or the right edge, like we do with the right sum. We're going to use the middle of the interval to do this. So again, if I was going to estimate the area from 0 to 4, so estimate all this area in here, except for that part, then I could use a midpoint sum to do so. So maybe I split this up into 2 subintervals just to make it easy on us. So I would say my first interval goes from 0 to 2, and my other interval goes from 2 to 4. So I would actually use the height at the midpoint. So for my first rectangle, I would not use the height based on the left edge, like that. I would not use my height based on the right edge either. I would use my height based on the midpoint. So the midpoint of that first interval is 1. So I would use this height up here to determine the height of my rectangle. So my rectangle would look, I'll try to draw a good one here. My rectangle would look like this, approximately. Yeah. We'll go with that. Okay, so you can see here that there's parts of the rectangle that are above the graph. There are parts of the rectangle that are below the graph. So the accuracy is not as easily defined here as it is with the left sum or the right sum. And then, of course, the midpoint from 2 to 4 is 3. And so I would use the height at 3, and that is approximately right there. So again, I would use a rectangle based on that height. So maybe, yeah, try that again. There we go. So maybe use that rectangle. And you can see that this rectangle happens to mostly be under the curve. Maybe there's one little part there where it's a little bit above. But these would be 2 midpoint sum rectangles. And once again, to approximate the area, we would simply find the areas of those rectangles and add them up, and that would be our estimate for the area. Okay, so in the first three examples, we used varieties of rectangles to approximate area. In the final way that we're going to approximate area, we're actually going to use trapezoids. So we call these trapezoid sums, and of course, trapezoid sums don't use left endpoint rectangles or right endpoint or midpoint rectangles. They use trapezoids. And the key formula to remember here is the area formula for a trapezoid. The area of a trapezoid is 1/2 times height times the quantity of the base length plus the other base length. So there's 2 base lengths in a trapezoid. The challenge here with trapezoids is the classic way that we've seen trapezoids represented in maybe a geometry course where this is the height, maybe this is base 1, that's base 2 perhaps. And you could find the area of the trapezoid. What you're going to find here, the way we use trapezoids to approximate area, is the trapezoids actually get rotated so that they look more like this perhaps, where the height is here, this is base 1, base 2, right? So this trapezoid has just been rotated up onto its end, and that's how we're going to use trapezoids to approximate the area. So I can approximate the area from 0 to 4. I could use trapezoids to do so, and I'll split it up into 4 subintervals like I've done on a couple of the others. My first trapezoid would look like this. It would come up to this endpoint, it would come up to this endpoint, and we would connect those. That one almost looks like a rectangle, doesn't it? Next one won't. The next trapezoid would go all the way up to here, and then we'd connect those 2 points. The next trapezoid would come up to here, and we'd connect those 2 endpoints. And then the last one, I guess this trapezoid would really, honestly, end up looking like a triangle, wouldn't it? It would come all the way down to here, where I guess one of the bases would actually be 0. In any case, the way that you would approximate the area here is simply to find the area of this trapezoid using the area formula, and then find the area of this trapezoid using the area formula, so on and so forth until you found all the areas of the trapezoids, hopefully not too many of them, and then you just add up all those trapezoid areas, and that would be your approximation for the area between the x-axis and the curve. Okay, so like I said, key formula for you on trapezoid approximations is that. You'll definitely want to have that memorized, and when you come to class, we'll try to use these to start estimating areas. Hope you have a great day. We'll see you in class.